Hi, everyone. I'm Erik Brynjolfsson, and this is the Stanford Digital Economy Lab Lunch Seminar. Welcome. Today, it's my privilege to introduce Danielle Lee, our speaker, who's going to be discussing hiring as exploration. Danielle is a professor at MIT, where she studies how data and analytics can be used to make better decisions about people and ideas. She's got her PhD from MIT and a bachelor's degree from Harvard. She's also taught at Harvard Business School and the Kellogg School. If you have questions for her, please use the Q&A function here in Zoom, and I will read those and relay them on to Danielle. Danielle, welcome. Please take it away.
Thank you so much. Let me share my slides. Okay, great. Hi, everyone. Thank you so much for having me. This is joint work with Lindsay Raymond, who is a fantastic PhD student at Sloan, and Peter Bergman, who is at Columbia. So this paper is about the role of algorithms and algorithmic design in the hiring process. So hiring is obviously one of the most important decisions that organizations make. And those decisions matter for productivity from the firm side and for access to opportunity from the worker side. So this is an area in which there's been growing excitement about the potential for machine learning-based tools to improve the process, to improve screening. That excitement comes from a lot of research coming out of this lab and others as well, showing that kind of machine learning can be used to improve the quality of decision-making relative to human practices across a range of settings. So examples in hiring, in criminal justice, in medical diagnoses and caretaking. And as a result, there has been an increased supply of third-party firms offering machine learning-based recruiting tools and an increased demand for these tools across a lot of firms. At the same time, there have been growing concerns about algorithmic fairness and bias, and obviously different fields use these terms to mean different things, and there are a lot of nuances involved when we're thinking about algorithmic bias. But there has also been empirically a growing number of papers documenting situations in which algorithms are directing fewer opportunities and resources to people from traditionally disadvantaged groups. So what we want to do in this paper is we want to understand, can we build productivity enhancing hiring algorithms that also distribute opportunity more broadly? So to kind of motivate this paper, I want to start by talking a little bit about how traditional modern hiring ML works. So for the most part, hiring machine learning tools, as they're being currently used now, are based on supervised learning. So what that means is that we are going to start with some kind of historical data set of applicants, and it has information on their covariates. So that could be their work history, their education history, so on and so forth, and some desired outcomes. So for instance, did they do well on the interview if we interviewed them? If we have data on when someone is hired, did they do well on the job or not? So using that historical training data, what we're going to do is we're going to build a predictive model, and then we're going to apply it to the people that we see in the future. So this is an approach that works well in some sense if we think that we've essentially reached the end of history. So any applicant that we might see in the future, we can go into our historical training data set and find representative applicants with similar covariates so that we can make an accurate prediction for that new person that we see. And also we have to assume that the environment is stationary enough so that the predictions that were true yesterday are going to continue to be true today. And there are a lot of reasons why we think that that might not be true of hiring. So obviously not all groups are well represented in the training data set, and that can be because training data are based on historical hiring practices. And so if you never hire people or you never interview people from certain groups, you're going to have less information about them. It's also the case that the predictions we made yesterday might not necessarily apply today, both because supply and demand for skills could be changing over time. So the set of women with computer science degrees 50 years ago is different from the set of women with computer science degrees today. And you can also imagine that what it takes to do a job well also changes. So for instance, online teaching requires a different set of skills than in-person teaching. And so the central message of this paper is that instead of thinking about hiring as a static prediction problem, what we should instead do is think about hiring as a dynamic learning process where firms are trying to learn about which workers might be appropriate for their company over time. And so in that world, what we should think about hiring as a bandit problem. So a firm at any given point in time can think about whether they want to exploit, which is to say, let me take the data I have so far and pick the people I think are good based on that data. Or I can engage in exploration, which is to say, let me pick some people that I know less about, because in this way, I'm going to learn about their quality and that can improve my decisions in the future. So bandit problems have been well studied in statistics and in computer science. And it's known that the optimal solution is going to have some balance of exploration and exploitation. And the thing is that traditional supervised learning approaches, what they do is they are exploitation only. They take the existing current data set and they try to pick the people who are best in that data set, but they don't account for the fact that we might want to learn about the future. So what we want to do in this paper is we want to do something different, and we're going to introduce a contextual multi-arm bandit, which I'll describe in a bit more detail in a few slides, that's going to allow for exploration. And basically the idea is that the algorithm is going to learn from the choices that it makes, and it's going to know that it's learning from these choices so that the value of future learning is going to be incorporated into the selection decisions that we make today. So bandits are not new. They're used in a lot of ML applications. Reinforcement learning, for instance, is a large class of ML tools that are sort of more sophisticated. And these are the kinds of things that we use to teach cars how to self-drive because they're constantly trying to encounter new situations. What we want to do is we want to apply this in the context of hiring. So the paper does a few things. The first is that we are going to build a resume screening algorithm that is going to value exploration. So the algorithm is, you shouldn't think of this as an algorithm that helps the firm decide who to hire or not. It's helping the firm do the initial resume screen, which is of all the applications I get, which ones should I select for an interview? The way that we're going to design this algorithm, we're going to train the algorithm, is that its goal is going to be to maximize the share of people who we interview who actually do well in those interviews and who end up hired as a result. We're going to do this by using a contextual bandit version of a classic upper confidence bound algorithm, which I'll describe in a few slides. And we're going to train, and our context is going to come from administrative data on professional services hiring at a large Fortune 500 firm. So these are business consultants, financial analysts, and data scientists. So once we sort of have built these algorithms, we want to understand how they're going to behave. And so we're going to compare sort of two main aspects of behavior: the demographics of the people selected by the algorithm, and the quality of the people selected, where quality is going to be measured as how well you do on the interview as measured by whether you're hired. So we're going to take data from this firm. With the first half of the data, we're going to sort of train our models and use that to sort of build our models. And then the second half of the data, we're going to try to understand how our models behave differently. So we're going to compare several different kinds of algorithms. The first is not an algorithm. The first is what the firm is actually doing. So they're making interview decisions using human recruiters. The second thing we're going to compare that our sort of exploration-based model is, we're going to compare it against what traditional supervised learning algorithms will do. So we have two versions of that. One is a supervised ML that's trained on a static training data set and we never update it afterwards. And then we also have a version in which we update it afterwards, but it's not actively exploring. So one thing I want to make clear is that, unfortunately, this is not an experiment. So we did not actually implement these algorithms live. And what that means is that there's going to be situations in which the algorithm is going to want to interview someone who was never actually interviewed in practice. And because that person was never interviewed, we don't get to see what their true hiring outcome would have been. And so the paper is going to have a fair amount of econometrics in it to try to get around that problem. And I'll discuss a little bit of that, but I'm happy to talk more about it in the Q&A. So we have two extensions, which I'll hopefully have a chance to talk about. The first is we're going to think about learning. So we are going to show you how the algorithms behave on the data that we actually see. But you can also imagine situations in which, how would these algorithms behave in a world where applicant quality is changing more, the labor market is evolving more. So that's going to allow us to think about the role of exploration in situations in which learning is more important. The second thing we're going to do is we're going to think about demographics blinding. So the main algorithm I'm going to show you today has access to protected demographic categories, race and gender. And as a result, that algorithm can, and it does, engage in disparate treatment, which means it will treat Black applicants different from white applicants on the basis of race. That is a legal gray area. And so what we can do is we can also run versions of these algorithms that don't have access to these inputs and think about how they would do. So to preview the results.
Danielle, just one quick question on that. the demographic inputs, is it like directly labeling the race of this person, or what about suggestive information like, I was president of the Black Students Association?
Yeah, so the demographics inputs we have are the actual labels provided by the worker themselves, the applicant themselves. We don't have information on kind of like things like the Black Students Association because we have the CV, but the way that they use the CV is that they use a talent management software that strips a lot of that information out. If it's the case that we could sort of perfectly back infer race using the other variables, then our race blind model should be pretty similar. We aren't going to be able to do that fully. The algorithm isn't able to do that fully, so the results are going to be a bit different.
Okay.
Any other questions?
That's it for now.
So let me just preview the results. So the first thing we show is that relative to what the firm is currently doing, they can improve both their hiring rates and increase representation of underrepresented minorities if they use an exploration-based ML tool. So our upper confidence bound model, that's going to increase the predicted hiring rate. So this is our quality measure relative to what they're currently doing from about a 10% hiring yield to something closer to 30%. Moreover, when we use this model, this UCB, it increases the share of Black and Hispanic applicants who are interviewed from about 10%, which is what they're currently doing, to about 24%. And it increases the share of women who are interviewed from 35% to 40%. The second main result that we have is that the type of algorithm matters. So our static and supervised learning based algorithms, they're going to provide similar improvements in hiring rates, but so sort of similar improvements in quality, but the way they do it is that it decreases the share of Black and Hispanic applicants who are interviewed from 10% to what the humans were doing to about under 5%. In situations in which there is sort of greater changes in applicant quality, when we're sort of simulating differences in learning, the value of exploration is going to matter more in that environment. So in our existing data, the updating supervised learning, they perform sort of similarly well relative to our exploration model. When there are greater changes in applicant quality, the exploration-based model is going to learn a lot faster. So what I'm going to do is I'm going to start by talking a little bit about our setting and the nature of the jobs that we're looking at. Then I will spend a few slides talking about how we construct our algorithm. And then I'll go through our results, our main results on sort of diversity and quality. And then we'll talk about the extensions. So we look at professional services hiring, and this is a setting that has struggled with diversity. So there are a lot of firms that are interested in trying to find ways to recruit a more diverse workforce. This is a picture of a summer intern class from an investment bank. So this is different from our actual firm, but I think it's a representative photo of some of the representation issues that the industry faces. The second thing that's relevant about this setting is that this is a setting where the initial interview decision is very important. So our data firm, which is similar to many firms in its sector, is overwhelmed initially with options. So they post their openings on all sorts of platforms, and there's lots of inbound applications. So they see about 200 applicants for every hire that they make. And 95% of those applicants are screened out in this first cut prior to the interview stage. So these decisions are made by human recruiters who have very limited information. So they do a sort of a resume review, and they do it quickly. So they're going to see information on demographics, work and education history, depending on the time that they applied and the software that they used. Often they don't see a cover letter, they don't see club affiliation. Sometimes they do, sometimes they don't, but often they not. And this is a setting where the decisions matter. So for the firm, it's very easy to pass over qualified applicants when you're rejecting 95% of people in this way. And it matters for these applicants in the sense that these are good jobs, and you see applications coming from around the world and across the socioeconomic spectrum. And so to get one of these jobs is to kind of get a foot on a sort of a career ladder that allows for a lot of mobility. So what we want to think about is
Danielle, can you say a little bit about, so that they're passing over some qualified applicants. They also may occasionally be hiring some unqualified applicants. Can you say a little bit about what your sense is of their payoff function? Is it more costly for them to miss somebody who could be a star, or for them to hire somebody who doesn't work out?
Yeah, so we talked a little bit to the firm a little bit about this, and actually, I think let me actually, can I just? It's sort of exactly this question, so let me sort of take this slide in general. Um, but so we sort of talked to the firm about what their objectives are, and you can imagine in general the firm having lots of objectives. So one possibility is that they want to kind of fill the slot. So in that case, they want to interview people who are kind of above the bar in some sense. Or you might want to find superstars, in which case you're willing to sort of take some risks on other dimensions if this person's going to be great, conditional on showing up. Or you might want to avoid disaster. So you want to avoid people who are going to sort of hired and then commit fraud, for instance, or be sort of, be fired for other reasons. And so what we're going to do in the paper is we're going to focus on, when we design the algorithms, the objective is going to be sort of essentially to fill the slot. We want to interview candidates that have a chance of being hired. We come at this for a couple of reasons. The first, obviously, is a data constraint. We have much more information on how well you do on the interview relative to how well you do on the job, conditional on being hired. So we don't have enough data to train that. We also talk to the firm about what they care about. And for a lot of these positions, so between avoiding disasters or finding superstars, they prefer to find superstars. But what's also very important to them is to hire in an efficient manner, because the cost of interviewing isn't zero. So this is a setting in which when you do an interview at this firm, consultants who could otherwise be billing clients are now running case interviews with you. And what the firm has said is that they have a lot of negative interviews, in the sense that 90% of the people, so you reject 95% of people, but then of the people you interview, you also 90% of them don't end up being hired. And so that takes people away from productive work. And what they would like to do is to find a way to sort of fill their kind of interview class without expending the same number of resources. And that would be valuable to them as well. So what we're going to do is we're going to sort of train the models to do that. And then I'll have a little bit of data to show you that the models trained to predict that also seem to be kind of okay on these other dimensions. Does that answer your question?
Yeah, that's very helpful. I mean, on the point about the job performance, I mean, ultimately, presumably what the firm cares most about is that these people work out well. Are you in the process of gathering more data on that? Or I mean, in a sense, one way to interpret this is you're finding people who are going to interview well, which may be correlated with perform well, but it's a slightly different question.
Yeah, so we have, we're trying to get more data. The firm is COVID busy. So we have some data on people who are hired. So we have information on their performance rating 6 months into their position, and information on whether they've been promoted to that point. But we have data on 230 applicants for this, and so it's not that large. Ideally, we would get sort of another draw of data so we can kind of update it.
And there's an inherent sort of censoring, as you mentioned earlier in your talk, that, I mean, they're not going to hire everybody, so you don't know how some of the people who didn't get hired would have performed, and just like they're not interviewing everybody. So there's kind of an inherent, even no matter how much data you gather from the firm, you're never going to get the full experiment.
Yeah, and so that's also true of the interview data. So in the paper, which I probably won't talk about too much, we have an instrument, which is sort of this judge's instrument for leniency of the people that do the initial screening. So we can get some instrumental variation in whether you are interviewed, and we're going to use that to do a variety of things to test for selection on observables. Mm-hmm. We could, in theory, do the same thing on the hiring end, but at the current state of the data, we just don't have enough variation.
Yeah. No, that's great. Okay.
Yeah. Okay, great. Okay, so let me sort of talk about how we think about resume screening from the perspective of thinking about it as a contextual bandit. So you think about every period, the firm is going to see some applicants, and it has to decide between, so contextual bandit problems are, so you like multi-arm bandits, you pull one arm versus another. So in here, for every applicant we see, the arms are whether I interview this person, and if I interview them, I pay some cost C. The other arm I could pick is I don't interview them, in which case I don't pay any cost. The quality here, again, is someone's hiring potential. So this is a potential outcome that exists for all of us. So all of us have a variable, which is if we interviewed at this firm, would we be hired? So would they give us an offer, and would we take the offer? And so the firm's reward is going to be given by the hiring potential of the applicant if they interview them, minus the cost of interviewing them, or zero otherwise. So all of this so far is a standard bandit model. What makes this a contextual bandit is that before making the decision about whether to interview someone or not, the firm is also going to see some additional covariates, which in our case are going to be CV variables like work history, demographics, and education history. And these are contextual variables that predict the relationship between the action I take, interview or don't interview, and the reward I get, which is the worker's hiring potential. And the firm is going to want to maximize the sum of these rewards over time. And in computer science, this is often referred to as minimizing regret. Okay. So in general, what I should say is that contextual bandits, there's no sort of generic optimal solution to them, but there's sort of different classes of solutions. So one possibility is the greedy solution. And so what that means is you sort of pick people based on who you think is best given your current data. That's what supervised learning does, and it's suboptimal. And then there are a variety of algorithms that computer scientists have developed to approximate kind of optimal solutions to this problem. We're going to be using one of them, which is the upper confidence bound algorithm. And I'll talk about that when we go through the math on the algorithms. Okay, so our data come from this firm. We see about 90,000 applicants to this firm between 2016 and 2019. We're going to divide this data into an earlier training period and a later testing period. The reason we do this is we want to sort of mimic the idea that a firm might build an algorithm based on their historical data and then apply that algorithm going forward. So we're going to see information on whether someone's interviewed and if someone is hired conditional on being interviewed. And we're going to have a variety of predictors: demographics, education, work history, referral status, and some information about the job postings. So we are going to first build kind of a traditional supervised learning algorithm. We're going to be using—
Danielle, let me just ask a question. I guess it's a good time about the variables, the data you have. Kalinda Ukinawa asks whether the study takes into consideration the criteria used to select promising candidates. For instance, if the criteria is that candidates are from the top 20 universities as opposed to historically black universities, the pool of candidates may already be non-representative and lack variation for exploring the full pool of talent there. So is that one of the— can you say something about the pool in that sense?
Yeah, so I can show you some information about the applicant pool. We checked actually specifically on how many applicants there were from HBCUs, and there are some. It's not, the applicant pool is actually majority Asian. It's about 58% Asian. It's 9% Black, 4.5% Hispanic, and about a third, 30% white. The firm has an initial sort of screening rubric. They didn't give us there wasn't sort of like a specific kind of like diversity preference built into that rubric. And so that wasn't something that was kind of like officially codified in their hiring process. But what we're going to be able to show is that even amongst the pool, so we're not saying that the pool is necessarily like as diverse as it could be, because one of the big challenges is just getting people to apply. But when I look, one thing I did was I just like literally look through some of the applicants and what their CVs were like and what their race was. There are a lot of Black applicants from good schools who are being passed over for interviews in this data that our algorithm selects that were not selected by the humans. So like there's like lots of like Black applicants from Princeton, for instance, who didn't get an interview.
Mm-hmm. Okay.
Okay. So what we're going to do is we're going to start off by building kind of a traditional supervised learning model. And so what we're going to do is we're going to take the training data set and we're going to basically predict someone's hiring potential conditional on being interviewed using these X covariates. I should just say that the model is not that great. So as a predictive, it has an area under the curve AUC metric of I believe it's 0.66. And so basically that means we correctly categorize about 66% of the time. And if you keep in mind that chance is 50%, I don't want to say that this is a great model. I want to say that this is a model that we built off the shelf. And even this model is going to have some nice properties relative to what the recruiters are doing. So we're going to have two versions of this kind of standard supervised learning model. The first is a static SL, which is to say I'm going to make the model, I'm going to keep those coefficients, and I'm going to apply it throughout the test period. The second thing I can do is I can say in period 1 of the test data, I'm going to select the applicants that have the highest scores based on their predicted quality right now. And then I'm going to take their hiring outcomes, I'm going to add it back into the training data set, and I'm going to rerun my model so that in the next period, I'm going to have a new model that incorporates the outcomes of the people I just chose. Now, there's a big caveat in the paper, which we discuss more, which is that in a live experiment, what would happen is the algorithm would say, hey, you should interview Anne, and then we would actually interview Anne, we would observe Anne's outcome, and we would add the data. But what happens here is that because it's not a live interview, we can only update the model with Anne's outcome if Anne is actually interviewed in practice. And so if the algorithm wants to interview someone that the human doesn't actually interview, we can't update the data. And so that could potentially create potential biases or other kinds of problems. The paper is going to use sort of this instrument that I discussed to show that this doesn't seem to create, there's no evidence of selection on unobservables. So the way you should think about this is that this is going to decrease the rate of learning rather than biasing the estimates per se. So the second class of models we have is sort of this.
I mean, maybe it's worth just briefly explaining. I think that instrument's kind of neat, and I think I get it, but it might, you explained it pretty quickly. Maybe just explain a little bit about how that works, the leniency, how that helps you overcome this issue.
Yeah, so let me, is it okay if I put this off? Because I do have some slides on the instrument.
Oh, okay, good, great. Yeah, do it then.
But so just keep in mind that there is a selection bias, and I owe you like an explanation of the selection bias. So the second algorithm, sort of class of algorithms, is exploration-based algorithm. And essentially what happens is at the very beginning, all these models are trained on the same data. So on day one of the test data, they have the same beliefs about what the quality of the applicants. But what this generalized linear upper confidence bound UCB model is going to do is it's going to score applicants differently. So before, what happened is that I scored people based on my expectation of their quality, my expectation of their hiring potential based on the data I had. What the UCB is going to do is it's going to add this additional term, which is an exploration bonus. And it's calculated following this other paper. And the reason why we use this form is that this paper kind of shows it has some optimality properties with respect to being asymptotically regret minimizing. And essentially what this is, this exploration bonus is that it's a standard error. And it says that I'm going to give you a higher bonus if your covariates X are very different from the mean of the covariates I've seen before. So if you look different from the people I've seen before, and this is a precision matrix. So what that means is that I'm going to give you a bonus if you look very different on a variable in which everyone else seems pretty homogeneous. So if you have a weird college major and everyone has a weird college major, I'm not going to give you a really big bonus. But if every last person is a business major and you're a theater major, then I'm going to give you a big bonus for that. And what I like about this process is that the intuition is kind of nice. So we all know that the optimal solution to a bandit problem is to create some balance of exploration and exploitation. If I wanted to engage in exploitation, I would want to maximize purely based on expected quality, in which case I want to sort of maximize based on this mean. And if I wanted purely to engage in exploitation, I would just want to maximize on distinctiveness, just pick everyone who seems strange. And what the UCB is doing is that it's combining the two pieces. And in particular, the way it combines it is that, so we're adding a mean and then we're adding a standard error. So basically we're judging people based on the upper bound of the confidence interval associated with our estimate. So what this says is that if we see two people, we think they're equally good, as our sort of a guess, but one of them comes from a group that we know less about, their estimate is going to be noisier. And so we're going to give that person the benefit of the doubt. So it's often called, so UCBs are often kind of thought about as optimism in the face of uncertainty. And so one thing I want to note here is that there's no explicit preference given to demographic minorities in the way the algorithm is set up. So this is not affirmative action. There's a preference in the sense that if you are rare on some dimension, that could be race, that could be education, that could be lots of things, you're going to get a higher exploration bonus. So let me sort of briefly talk about the theoretical predictions.
Actually, one more question about the data in the setup. This is from Johan Gabler. Can you explain how you featureize each application? Do you do text analysis or do they provide information that's already structured? How do you convert the resumes into data for the model?
Super old school. So this is, there are a lot of people in the audience who do this in a far more high-tech kind of natural, like NLP kind of modified way. They gave us CSV information of like, from the sort of the talent management software they use, takes the CVs, converts it to a CSV, which they often use on the back end. Then we ended up with a list that's like University of Wisconsin, math major or whatever. And Lindsay and I hand coded it into sort of different categories. And what we did was we built the model, sort of checked for the predictability of the model, and we could have coded it further and further down, but we kind of stopped when we got to the point where our model wasn't improving. And so, for instance, we have information on whether you went to Michigan versus Wisconsin, but we didn't code that difference.
So, but you got CSV data. You didn't get like the resumes. the company, HR company did that. You don't know, did they hand code that, or did they scan it in some way? Was it, do people enter stuff in structured fields?
I'm not sure. I think that's also varied across time. So for some of the, my understanding is that for some of the positions, they saw PDFs of the CVs, and for some of the positions, it was processed by the talent management software, but we don't have a variable indicating which one is which.
Gotcha. Okay, thanks.
So with respect to quality, theoretically, it should be the case that in the long run, UCB, which is should minimize regret relative to exploitation only supervised learning models. It could be sort of selecting worse candidates in the short run while it's exploring. The issue in our data is we don't really know what constitutes long run. We're not seeing infinite applicants. And so the question about which one is better is still going to be, it's theoretically determinate, but it's empirically indeterminate. With respect to diversity, here we're going to measure diversity as race and gender. There are no predictions for which one should lead to more diversity. So again, the UCB doesn't have an explicit preference for demographic minorities, but it's going to explore, and it could potentially explore along race variables. It could also explore along education and other kinds of variables. But over time, what's going to happen is that as I know more in the long run, as I know more and more about these candidates, I'm going to have more and more precise estimates. And that means these confidence intervals are going to shrink. And so the long run difference between these supervised learning models and these UCB models is going to be driven by their differences in beliefs. And their differences in beliefs are shaped by the path of applicants that they saw. So it could be the case that I explored and I chose more minority candidates and I found that they were great. And so in the long run, I'm going to pick more of them than supervised learning would. But it's also possible that I could explore, find out that they're terrible, and pick fewer than supervised learning would. And so these are all kind of open empirical questions. Okay. So now let me talk about the results. So there's a lot of results in the paper, and I'm going to try to focus on a few of them for the purposes of this talk. So I'm going to focus on the results with respect to race. I'm going to talk about the diversity results first, because we observe race and gender regardless of whether you're interviewed. So it's a little bit econometrically more straightforward. And the second piece is we're going to think about hiring likelihood. So this is this potential outcome. Would you be hired if you were interviewed? And this is something we only observe if you're actually interviewed in practice. And so what the paper is going to do is that we're not going to have a perfect answer to this. We would have to have an experiment to have a perfect answer to this. So instead, the paper takes three different approaches, and we get the same answer, and the approaches are kind of complementary. So that's what I'm going to rely on. I'm going to show you the first two, but I'll talk about all of them right now. So the first possibility is I can just look at the set of people who were interviewed. Among those set, I actually observe their outcome. And so I can say which algorithm, which sort of approach ranks better within that set. So that essentially ignores sample selection. The other possibility is I can try to infer the quality of the machine learning selected applicants who weren't selected by the interviewer by looking to see similar people who actually were interviewed and then using their outcomes to back out what the outcomes would have been for these other people that we didn't select. So that's going to require us to believe that there's no selection on unobservables. And then finally, what we can do is we can kind of look at the margin and ask, can we shift ML human hiring practices closer to the ML hiring practices, and would that improve things? And to do that, we're going to sort of use this leniency instrument, and that's going to allow for selection on unobservables. I'll talk about this a little bit briefly, but the paper has a longer exercise that I'm going to skip. And then lastly, there are three extensions. I'll talk about the learning one, and if there's time, I'll talk about demographics blinding. Erik, do you have a sense of how much time I have left?
Yeah.
For the 40 minutes.
We've got about maybe 10, 15 minutes, and then we'll go to open Q&A.
Okay, sounds great. Okay, so let me talk about the diversity. So the diversity is basically, we see the number of applicants who are interviewed in practice. We're going to interview the same number of applicants, but rank them by different models. So as I mentioned before, panel A here is the applicant shares. And so this is a data set in which most of the applicants are Asian. So that's a combination of Asian Americans as well as primarily sort of people from China and India applying, mostly Asian Americans. And then about 30% are white, 9% are Black, 4.5% identify as Hispanic. Panel B here is the demographics of the set of people who are actually interviewed from this pool. So you can see that the Hispanic share stays similar. The white share kind of expands. The Asian share is sort of similar, and the share of Black applicants who are selected goes from 9% down to about 5%.
So that's a much bigger Asian and smaller share than that photograph you showed, I think. I didn't look carefully.
Yeah, yeah. So well, to be fair, those are so these are, there are a lot of kind of quantitative jobs for which, the applicant pool is just is more Asian.
So, yeah, okay. So this is what it is. It just, that photo was for a slightly different company you mentioned, and maybe job.
Yeah, so fair enough. So I think if you look at the business consultant positions, there will be more white applicants in those positions relative to the sort of the financial analyst and data scientist positions.
Yeah. Okay.
So in this paper, we're also not treating Asian applicants as sort of minorities.
Okay.
So the next two results I'll show you are the shares for this traditional kind of supervised machine learning approaches, which is sort of the static SL and the updating SL. Okay. So if we just do the static SL, which is to say that we're going to train the data set on the training data and then we just use it, what we see here is that basically the share of white applicants that we pick expands by quite a bit. The Asian share goes down a little bit, and then the Black and Hispanic share combined goes down to less than 3%. If we do the updating SL, we see a version of this. It's a little bit less stark, but sort of a similar breakdown. And then contrast this now. So now the new panel D is our exploration-based model, and I'm just leaving the updating SL up as a benchmark. You see far more representation of Black and Hispanic applicants, a similar share of white applicants relative to what humans are choosing, and then substantially fewer Asian applicants being selected for an interview. So there are a few things happening here. So Black and Hispanic applicants are receiving higher exploration bonuses. This is driven by their race per se, but it's also driven by their correlation with other variables. So they look heterogeneous on other variables as well.
Can you say how much in each of those like if you took race out entirely, how much of a bonus would they still get? Is it a big part of it or a small part of it or equal part?
It's I can show you in the race blind results. So the race blind results are still going to have more Black and Hispanic applicants relative to what the humans were doing. I don't have a percentage number offhand, but I can show you.
Yeah, that'd be great.
Yeah. Okay. So you can imagine a bunch of things happening. One possibility is I explore at the very beginning, I realize these applicants are terrible, and then I stop doing it. And then when I average across the entire sample, I still get this elevated share, but it's coming from a decline. That's not the case in our data. So the share of Black and Hispanic applicants selected over time is pretty stable. The beliefs about these applicants are pretty stable. So it's not the case that I start in the beginning and then I learn that they're bad, or I increase my share. So I mean, obviously the demographics are different, but a key question that we're interested in is what this does to the quality of applicants who are hired. So let me start with the first approach, which is just look at the set of people who are actually interviewed. And so for these people, I actually observe their hiring outcome. And so I want to ask what score, so the human score, the supervised learning scores, or the exploration scores are kind of best at identifying the candidates that are actually hired in practice. So the key issue here is that we don't observe a human score. We don't observe the rank. We just observe whether they were picked. But we can try to back this out by using kind of machine learning to predict whether someone would be interviewed given their covariates. And so we're not trying to predict whether they're hired, we're trying to predict whether they're interviewed. And so we can kind of get a reasonably accurate model of that. So we sort of correctly categorize about 76% of the time. It's not perfect, but just kind of keep that in mind. So when we do that, let's just focus on panel A for a moment. The x-axis here is the score. So these are people who have covariates that make it very likely for them to be selected by the human for an interview. And these are people with covariates who are unlikely to be selected. Again, these are all people who are interviewed. And you see that among this set, there doesn't seem to be much of a relation. If anything, there's a negative relation between how much the human wants you and whether you're likely to be hired. Whereas in contrast, all of the other algorithms have a positive relationship in terms of they're more predictive of quality within the interviewed sample. So one possibility is that humans are prior.
One question, just to help understand the first chart, the human chart. How do you get people on the far left of that? Obviously, there's more people on the right side of the chart, but if the human didn't want to interview you, why are you in the sample?
This is the model. So this is our, we're trying to predict whether humans are interviewing you. And so we're not going to get a perfect prediction. So there's some people who look like they were. So it could be that these people were sort of secretly good on unobserved dimensions.
Okay, so the model predicted that they would not be, that the humans would not want to interview them, but they still somehow got interviewed. Okay. But that would, I mean, I guess you said that there's not much evidence of it, selection on observables, but if there were unobservables.
So if that's so selection on observables could be one possibility for this. I haven't shown you evidence on that, but I will show you evidence on that. And then just in general, if you pick 20% of people or 10% of people or 5% of people, there's just going to be variation, even if you're going down the distribution in a straight line.
Right.
Okay, so one possibility is that humans are prioritizing some other aspect of quality. So these are people who maybe aren't likely to be hired, but if they are hired, they do really well. So for instance, if you pick people with exceptionally strong CVs, they might turn down the job, in which case they won't be hired. We don't have a great way of addressing all of these things, but one thing we can say is just among the very selected set of people who actually are hired and for whom we have information, we can just try to correlate this. And so in the first panel, this is the correlation between the human score as we predict it, and whether or not someone gets a top rating conditional on being hired, performance rating, or whether they're promoted. And so I mean, again, these sample sizes are small and they're selected, so I don't want to lean too much on this, but it doesn't look like it's a positive relationship. We can contrast and do the same exercise for the UCB. And here, we don't have that great a predictive relationship either, but at least we see a positive relationship with promotion. So there's no evidence, what I want to say is there's no evidence here that humans appear to be substantially better on these other dimensions. So now let me think about the full sample. So one possibility is that maybe what the humans are doing, how they're contributing, is they're making sure the worst applicants are never interviewed to begin with. And so there might not be a predictive relationship among the set of interviewed people, but on net, it might be beneficial. So what we ideally want to do is we want to compare the expected quality of people who are selected by the machine learning algorithm versus the quality of people selected by the algorithm, by humans, but we only actually observe the human selected set. So what we do here is we're going to use inverse propensity reweighting. And basically what that's saying is that we're trying to infer this thing we don't observe using information on the people we do observe. And so we're basically going to reweight the hiring outcomes of interviewed people to give more preference to interviewed people who have covariates that make them look like they were more likely to be selected by the machine learning process. So we just kind of reweight the things. The key assumption here is that there's no selection on unobservables. In most labor economics contexts, that is a very bad and scary assumption to make. I want to sort of, and we'll do some IB stuff, but I want to kind of argue that just intuitively, it's not too crazy in our setting, because these are recruiters who are going through thousands of applications very quickly. They see CV information, which is also the information that we observe. They don't interact with the candidates, and we observe whether or not the candidate is a referral. So the kinds of things that you should think about is like a potential unobserved selection is I'm a recruiter and I went to this college and I see that this person went to Michigan instead of Wisconsin. I'm able to I prefer that person, or I'm able to sort of better read their CV. It's not something like I met this person and I thought this person was crazy versus not. Okay. So when we adopt this this hypothesis, this assumption of selection, no selection on unobservables, we see that all of the algorithms appear to do better in terms of quality, and in particular, the algorithms that update. So the UCB, as well as the updating SL. So the actual hiring yield is about 10%. And here we're sort of predicting hiring yields of about 30 to 35%. So what that means is that the people that have high ML scores that are being selected to be interviewed are doing well, and that there are lots of other people who are in the applicant pool with similar covariates that we would also predict to do well if we simply picked them. So obviously one concern here is that humans might be positively screening. So maybe the people who are selected by the humans are somehow unobservably better than the people with similar covariates who are not selected. There's a reason why someone didn't get interviewed. And that would lead us, if that were the case, it would lead us to sort of falsely assume that there are all these leftover people in the applicant pool who will be just as good. They were going to be worse on some dimension, and the human knew it, and the machine learning algorithm doesn't know it. So what we're going to do is, well, I can show you this a longer exercise in the paper, but one thing I can show you is we can try to test for how much selection on unobservables there is. And the way we're going to do that is we're going to use random assignment to recruiters. And so essentially what happens here is that in many settings, when you apply, you get assigned to a screener. And the screeners in our data, because they're people, there's just like a lot of natural variation in how lenient they are. So some screeners are going to be more likely to select the greater share of the people that they see, and some screeners are pretty strict. And so, there's some evidence in the paper about the IV kind of validity here. But the idea here is that let's imagine that you're a cohort of people that were selected by a very strict screener. So this is a person that assigned a higher bar. And if it's the case that humans have some kind of knowledge about unobservables, then it should be the case that the people who are selected according to a higher bar should on average have better outcomes than people who were selected by a more lenient recruiter who subjected people to a lower bar. So if we're sort of properly ranking based on quality. And so what we can see here, let's focus on panel A for a moment, is that there really isn't that much of a relationship between the leniency of the recruiter. So these are people who had a low bar, and these are people who had a high bar, and the interview outcomes of the people that they interviewed, the hiring, so whether they were hired or not. So if we don't control for anything, so we don't control for demographics, that is. So this is kind of comparing people who apply for the same job type in the same office location in the year. The people that are selected by the more stringent recruiters don't seem to have better outcomes. And if anything, maybe this line is positive, but it's not statistically significant. If we control for demographics, so we're controlling for race and education history and all this other kind of stuff, we see also a flat relationship. So there doesn't seem to be any evidence of selection on these unobservables or observables, actually, for that matter. So to summarize the main results, we can kind of think about plotting the outcomes of various hiring policies along two axes. One is the share of underrepresented minorities that they're selecting, and two is the hiring rate. So this is kind of the quality of the people. And let's say humans are here. What we have is that the updating supervised learning algorithm, which was sort of the Pareto better one, is able to sort of increase the set of the hiring rate of the people that we select, but at the cost of decreasing the share of Black and Hispanic applicants who are represented. So if you look at these two lines and you're an economist, it's often tempting to sort of draw the Pareto frontier here. And if we were to draw this Pareto frontier, one interpretation that would be consistent with this data was to say that humans are kind of engaging in exploration or engaging in affirmative action in a way that they're sort of willing to sort of trade off quality to expand demographic representation. But what our other result about the sort of the exploration-based algorithm says is that we can actually, relative to what humans are doing, we can actually sort of increase the diversity of the people who are selected, at least on race and also on gender as well, and increase the hiring rate. And so what that suggests is that the firm's kind of current recruiting practices are inside the frontier. And by using exploration-based algorithms, they can increase hiring yield and diversity. But that algorithmic design matters. So this is not something that you get for free by using an algorithm, any algorithm. And in fact, relying on sort of traditional machine learning tools is going to tend to decrease demographic representation. So I'm happy to sort of stop here and take questions. I can also talk about the extensions.
Yeah, there are a number of questions. Let me just pick one that just comes off of that last chart, which I think was a great way of summarizing things. You had a particular machine learning, supervised learning system, and different people might write different ones. I think you attributed the main difference between having the reinforcement learning versus machine learning. What about the hypothesis that someone else might have written a different reinforcement algorithm and a different machine learning algorithm and not gotten those same results? Like, how much do you think is specific to the people coding it versus the algorithm?
So I think
why do you think it might be the algorithm?
Yeah, so I mean, I think what we did was we ran a fairly standard kind of, we used like a logistic lasso kind of, so like a fairly standard off-the-shelf thing. We chose these in part to mimic the kinds of tools that are being used by firms that do machine learning. So hiring ML is not the vanguard of ML applications in the world. And so we're trying to sort of do something that many firms would use. Did we try I think we tried a very reasonable set of machine learning algorithms. It's possible that other exploration-based algorithms would have gotten something different. We did some variations on it, and it seemed like these results are fairly robust. I think another way of asking a similar question is, this is the result that we got on these data. If the data were different in some way, if the training data were different in some way, would we have gotten a different result? So you can imagine that the training data we have was selected by humans in one way. You can imagine it being selected in other ways. And that's something we can't say except for by running counterfactual simulations. And one of the projects I'm working on now is about kind of taxonomizing more generally how the relationship between data generating processes, the processes that generate training data, and the returns to exploration. One of the exercises that we do next in the learning situation, I'll just talk about it very briefly. Basically, we try to measure how much learning happens. And what we see here this is basically a simulation in which we imagine the quality of Black applicants increases. And I'm happy to give more details if someone wants to. But the idea here is that the learning, eventually updating SL will learn, but it learns rather slowly. And the reason it does that is because it doesn't pick many Black applicants. And because it doesn't pick up Black applicants, it doesn't learn that their quality is improving in the simulation. The UCB algorithm, because it's affirmatively trying to explore, it encounters more Black applicants, and therefore it picks up on that learning faster. And so this is the kind of thing that is important if the data are different, or if the set of applicants are different, and in particular, if it's changing a lot.
It's learning about those unusual characteristics, that some of which turn out to be very valuable, some of which not, and doesn't know until it tries.
Exactly. And one thing actually you can see the orange line here. So the green line is what it actually does. The orange line is what it would do if it acted only on its beliefs. You'll recall that the UCB had a belief section and a bonus section, an exploration section. So the orange line is what would happen if it was just beliefs. And so in the beginning, what you see here is that it doesn't think that Black applicants are very good right now, but it's still picking them because it's trying to explore. But then at some point, it actually begins to think that Black applicants are better than that are better, but it's not picking as many of them because it's trying to explore on other dimensions.
Right, or it finds some Black applicants are better, and it finds out which ones to focus on, I guess.
Yeah, so I mean, so in this, and I didn't sort of set up the simulation, but in this simulation, the quality of Black applicants is sort of increasing over this period, and the algorithms are sort of learning about that.
There's a question from Sarah Bana, who I think you know. How do you deal with people who turn down the job? Is hiring, is that being offered a job, or is that actually accepting the job?
It's offer and accept. So right now they're coded as zeros. We could actually run the models again on offer and sort of think about this.
Right. I mean, maybe some of the very best candidates are the ones that that have other offers.
Yeah. And so in that case, so I mean, if they were purely trying to do that, like let's imagine we're trying to get people from elite schools. And if we think that they're going to be really great on the job, then you would ideally so that's basically we're trying to have superstars, and we're willing to sort of take some loss. Again, our data aren't great, but right now, of the people who are being hired, it doesn't seem like there's that much of a relationship. But it's not like the people that they're managing to get are better once they.
Another question from Jonathan Hirsch. Does the exploration algorithm rank all feature diversity equally? You could imagine some features of diversity being more important than others. And yeah, I'll just leave it at that.
Yeah, so it does so based on, it doesn't rank them all equally, and it does so based on the variance that they have. And so we didn't sort of pre-plan, we didn't say you should weight education diversity more than you should weight like demographic diversity. But basically each of these covariates has some natural variance. And what the algorithm does is that it says that if people are more different on a low variance feature, then the bonus is more important.
Jerome Capirossi asked several questions, but let me pick one of them about soft skills and hard skills. I guess you said these were more quantitative position, but can you say something about the importance of different kinds of skills and whether the algorithm can take into account some of the softer skills that might not be in the data?
Yeah, so I mean, the algorithm doesn't have access to more features than the person. And so like in both cases, we never meet these candidates. And so it's hard to sort of infer social skills from the information either the algorithm or the human is being given, but they could weigh things differently. And so for instance, when you actually do the case interview, they are graded in the case interview on your quantitative skills, but also on variables like leadership and heart. And so to the extent that those factor into the ultimate decision to hire someone or to grant an offer, that's one way that potentially these algorithms could be better predicting these variables, but we haven't actually separated it into those pieces yet.
Johan Gabler has a similar, a related question, I guess, which is, what differences do you observe between the individuals selected by the human recruiters versus the Bandit or the other statistical approaches? Are there a few obvious covariates that the humans are failing to take into account, which they're not calibrating very well? I mean, did you look at sort of explainable, what's driving the differences?
We looked at them. There wasn't really like one thing that kind of stood out. So a lot of this is being driven by kind of the desire to explore. And so you see more humanities majors being chosen, for instance. You see more demographic diversity, obviously.
So more humanities majors are being chosen on the exploration dimension, right? But do they also turn out to get, be better quality?
Their hiring rates are similar. So my best kind of like summary of this is that essentially my guess is that the firm is somewhat it's not at the flat of the curve, it's just that there are lots of qualified applicants of lots of different types. And so you can go fairly deep on any distribution and still not lose too much quality. And so my guess is that in this setting, you can fill up this firm with white applicants who are decent. You can fill up this firm with Hispanic applicants who are decent. And what the exploration is doing is it's shifting which direction you're going.
Great. We're just about out of time. I'll leave the last question, just a broad question. Where do you see going with this research? Is ultimately, do you think that these algorithms are going to be able to help with both diversity and performance if they implement them this way? Is that something you see them implementing?
Yeah, I think the broadest thing that I've taken away from this research is that, and this is that there are a lot of problems that we treat as prediction problems when we should probably treat them as dynamic learning problems. And so I think hiring is a really good example of that. And so I think building algorithms that value exploration is an important thing that firms should do regardless of their preferences over diversity. And so that's something that I would like to sort of see implemented going into the future. I think organizationally it's a challenge because what happens is that you're sort of forcing organizations to put some weight on the future. And when you talk to people about why don't you sort of take more risks, like in PhD admissions, for instance, that there's a lot of conversation about risk, and we don't want to be stuck with the wrong person. And so there's this kind of positive externality that like accrues to people in the future, but that is paid today. And I think it makes organizations more conservative than they should be if you're sort of taking kind of long run.
I can see you definitely against. I mean, I was on the PhD admissions committee too over at MIT a few years ago, and I'll just tell you a quick anecdote. So one of the other faculty members, I won't say his name, really explicitly leaned against that with us, and I think it was very helpful and pushed us to go for the more risky applicant whenever we had one. I was just talking about this with my class. So in that group, the IT group, not the tech innovation group. We were explicitly kind of, when we saw two candidates, we would go for the riskier one, which obviously has benefits and costs. But it's something that I think you can imagine, depending on the culture, different organizations take into account in different ways, and it may be something that the algorithms, you can actually have a dial and set it and see how the performance turns out, as you have in this paper.
Yeah, no, and I think especially in like this setting, this is not whether you hire someone. This is literally whether you interview someone. You are still allowed to not hire them afterwards. Right. So I think that firms, I mean, there is a cost in the sense that people are interviewing and it takes time, but I think this is the kind of place where there's a lot of returns to exploration because you're not even stuck with these people if you don't.
Absolutely. I mean, finance theory, if you have option value, you're more likely to take risks. And with hiring, you do have some option value. If it turns out that your risk didn't pay off, then there's not that much cost in that you've lost an interview, but you haven't hired them permanently. So that seems like a reason for maybe being a little more risk-taking. Well, thanks a lot, Danielle. This was amazing, really interesting work and right on the cutting edge of humans and machines working together. And you see some of the trade-offs. So really appreciate you joining us today. Your paper's available, I think, on your website. I think we're going to put it on our website too, right?
Yeah, good.
So that's great. And let me just say for the audience, I didn't get to all the questions, but thanks for asking the questions. And next week we have Ben Golub from Harvard coming in, and he'll be talking about learning in networks. So we'll see you a week from today. Thanks very much. And thank you, Danielle, again.
Thank you.